Okay, now another modeling for first order and first degree differential equations. Actually, a very popular example, Newton's law of cooling or warming. Okay, in this uh, application for differential equations, we have to use this in the same way. Ruth and Briquet look like Briquet, but here uh, relation related with temperature. Okay, and small t is the time and capital T is the temperature. Okay, in equation in this equation, the mathematical formulation for Newton's empirical law of cooling or warming of an object is given by the linear first order differential equation, first degree, d capital T dt. Capital T is the actually independent variable here, and small t is the time. Okay, so temperature relation with the time. Where is the constant proportionality, and capital T is the temperature of the object for time t, which is greater than zero. And Tm is the actually ambient temperature, that is the temperature of the medium around the object. Okay, suppose there is an interesting example for this, cooling of a cake. Okay, uh, when a cake is removed from an oven, its temperature is measured at 300 degree Fahrenheit. 3 minutes later, its temperature is 200 degree Fahrenheit. How long will it take for the cake to cool up to a room temperature of 70 degree Fahrenheit? So here, 70 in Fahrenheit scale, the room temperature is what? 70 degree Fahrenheit. So if you want to solve these types of problem, that means using Newton's law of cooling or warming, so we have to use the first order and first degree differential equations like this. Okay, so using these differential equations, we can solve these types of uh, physical problem. Now, if we in from this identification, the mixed temperature is 70 degree Fahrenheit. So we must solve the initial value problem. dt d capital T divided by dt will be k into capital T minus 70, because ambient time is 70. Okay, at t equals to 0 time, t 0 temperature, the capital T what? Capital T 300 degree Fahrenheit. Okay, at time t equals to 0, initial time. Okay, at initial time, the temperature was what? 300 degree Fahrenheit. So T0, capital T0 equals to 300. And we have to determine the value of K, so that after 3 minutes, okay, after 3 minutes later, the temperature was what? 200 degree Fahrenheit. So capital T3 equals to what will be? 200. Now the equation 3 is both linear and separable. We can, by using variable separable method, we can solve the differential equation easily. So dt, t capital T minus 70 equals to what? Kt. Here's taking the integration on both sides. Integrating on both sides, what will be ln capital T minus 70 equals to, after integration with respect to time in right hand side, kt plus c1. C1 is the constant, integral constant. So capital T equals to what will be 70 plus c2 e to the power kt. When t equals to 0, capital T was what? 300 degree Fahrenheit. So just putting here time t equals to 0 and capital T equal to 300, we get the value of C2 to what? 230 degree Fahrenheit. Therefore, capital T what will be? 70 plus, just putting here the values, 70 plus through 230 e to the power kt. Finally, the measurement after 3 minutes, um, temperature what was? After 3 minutes, temperature was 200 degree Fahrenheit. So which can be leads to e to the power thrice k equals to 13 by 23. Just uh, finding the values of k using scientific calculator, we can write actually minus 0.1908. Therefore, just putting the value of k in this equation. This is the main equation. So capital T equals to 70 plus 230 to the power this. So we note that here the furnishes to finite solution capital T equals to 70, because at time t equals to if we take the limit t tends to infinite, if the time is infinite minutes, then the value of this from the equation 4 will be value 70, because this will become 0 at infinity. So yet the initiatively we expect the cake to reach room temperature after reasonably long period of time. So how long is, of course, that we should not be disturbed by the fact that the model 3, this is the 3, okay, this is the model, main model differential equation, initial value problem, Newton's law of cooling formula. So this model does not quite live up to our physical intuition. So part A and B of figure clearly show that the cake will approximately at room temperature in about what, half an hour. So at time t 75 degree minute will be this. So using small t here, small t equals to uh, in different time 20.1, we get the capital T values. Okay, so temperature of cooling cake, for example, for this example, this. Now the rate, the capital T is the along y-axis and small t, and that means minutes. In different minutes, we get this curve. This is the exponential curve. So this is a very nice example. But now we'll try to solve a problem. This one, 15, using the same procedure. A small metal bar whose initial temperature was 20 degrees centigrade and is dropped into a large container of a boiling water. That means increasing time, increasing temperature. So how long will it take to bar reach 90 degrees centigrade? If it is known that its temperature increases 2 degree in 1 second, how long will it take the bar to reach 90 degree centigrade? Now we are trying to solve this example. Now the modeling of ordinary differential equations in Newton's law of cooling or warming. That means the modeling of differential equations for Newton's law of cooling or warming. Actually, as the previous lecture, that means for growth and decay rate, same modeling for the first order and first degree differential equations. So for this example, we will use the fact uh, we'll use the fact that temperature, the boiling temperature, you must know, pressure is what, capital T equals to what, 100 degree centigrade, you must know, 100 degree centigrade. So from Newton's law of cooling, Newton's of laws, we can write ddt or T equals to what will be K into
লেখাটা সব ব্লার হয়ে গেছে
100. So from the Newton's laws, actually, uh, laws of cooling, we can write dt. The capital T is the temperature. That means dependent variable. Small t is the independent variable, time. Okay, equals to K to. So after solving this differential equations, you must know. After solving, we can write this differential equation by variable separable method. We can solve this. equals to k dt. Okay. So integrating on both sides equals to k into, therefore ln del t 100 equals to kt plus c1. Therefore capital T 100 equals to what will be? This will be ln c1. So ln e to the power 30 can be written as like this. Ln c1. So omitting ln from both sides, we can write del t equals to 100 plus c e to the power a t. This is equation number 1. So c is the actually constant. Constant. So now at t equals to 0, if time t is the 0, then temperature what was? Capital T 0 what was? 20 degree centigrade, right? And after 1 second, so 22 degree, after 1 minute, 22 degree centigrade. And this is actually given condition. So from equation 1, equation 1, 20 equals to 100 plus c into e to the power 0. That means equation number 2, and for t equals to 1, 22 equals to what? 100 plus c into what will be? E to the power k. T equals to. Now we can solve this for c. Just subtracting, we can find the so from here c equals to what? Minus 80. Okay. From here c equals to minus 80. I'm putting the values of c here. 22. That means k equals to what will be? K equals to, from here, ln 39 by 40, ln 39 by 40, which is approximately 0.0253. 0.0253. So from equation 1, therefore, from 1, capital T equals to what will be? 100 plus c equals to what? Minus 80, right? C equals to minus 80 to e to the power 0.0253 t. But there are negative sign, minus 0 point. Okay. So this is the equation number 4. Now, after raising the temperature, when capital T equals to 90 degrees centigrade, time will be time equals to what? Just putting capital T equals to what? Then from 490 minus 180 e to the power 0.0253 t. After solving this, or 80 e to the power minus 0.0253 t equals to 10. 100 minus 90 is 10. Or from here we can find 3t equals to 1 by 8. Taking ln on both sides. Taking ln on both sides. Minus 0.0253 t equals to ln 1 by 8. Therefore, t equals to, from here, t equals to, using the scientific calculator, 82.1 second. Okay, time will be in second. So now, when capital T equals to 98 degree, then from 4, this is the 4. Okay, then from 4, similar way, 98 equals to what will be 100 minus 82 e to the power minus 0.0253 t. Similarly, from here, 80 or e to the power minus 0.0253 t equals to 2. Therefore, e to the power 0.0253 t equals to 1 by 40. From here, we also taking logarithm on both sides. 0.0253 t equals to ln 1 by 40. So ln will be omitted. Therefore, from here t equals to, using scientific calculator, t equals to will be 145.7 seconds. 145 145 second. Okay, this is the result. So another example, modeling of ordinary differential equations in Newton's laws of cooling or warming. Two large containers, A and B of the same size, are filled with different fluids. The fluids in container A and B are maintained at 0 degrees centigrade and 100 degrees centigrade, respectively. So in a container, the 0 degree centigrade, and in B container, 100 degrees centigrade. Remember it. A small metal bar whose initial temperature is 100 degrees centigrade is lowered into container. Okay, container A. After 1 minute, the temperature of the bar is what? 90 degree. That means cooling, because temperature of A, what was 0 degree centigrade. This is why the bar is cooling. After 2 minutes, the bar is removed and instantly transferred to the other container. Okay. After 1 minute in container B, the temperature of the bar rises 10 degree. How long, measured from the start of the entire process, will it take the bar to reach 99.9 degrees centigrade? So now we'll try to solve this exercise for modeling of the first order and first degree differential equations. So now for this, for the solution of this example, using the for the container A, we can use the Newton's laws of cooling, dt1 by dt equals to k1 and capital T1 minus 0 degree, because the initial temperature was for the container A was 0 degree. Okay, this is why we are assuming the laws for Newtons like this. So whose solution can be written as T1 for first container. Okay, A. So T1 equals to C1 e to the power k1 t, and this is the first equation. First equation. Since at at 0 time, uh, temperature what at 0 time temperature was 100 degree. Okay, temperature was 100 degree, and that means the initial temperature of the bar, metal bar. The initial temperature of bar. Okay, 100. So from equation 1, we can write T1 equals to what? 100 equals to C1 e to the power k1 into 0. Okay, this equals to what? C1 implies C1 equals to what? 100. So putting C1 in 1, T1 equals to what will be? 100 e to the power k1 t. This is equation number 2. So after 1 minute, the temperature of the bar, what will be? T1 temperature of the bar, what will be? 100 into e to the power k1. Okay, t equals to 1. This is why. This equals to what was? After 1 minute, temperature decreased, and the temperature of bar decreased to what? 90 degree, equals to 100 e to the power k1. So from here we can find the value of k1 equals to 90 by 100 equals to k1 equals to what will be? Taking ln on both sides, we get ln 0.9. ln 0.9 k1 equals to. Therefore, equation 2 transform to T1 equals to what? 100 e to the power 0, e to the power ln 0.9 t. Okay, 0.9 t. So from equation 2, we get t into sorry, this t we must write t before ln, t ln 0.9. Okay, this is another equation number 3. Again after 2 minutes, after 2 minutes, the value of T1 will be 100 e to the power 2 ln 0.9. T value is what? 100 into 0.9 whole square, because L before ln 2 will become the power of 0. Power raised to 0.9. This is why approximately we get the value 81 degrees centigrade. Okay. After 2 minutes, the temperature increases. So the differential equation for the now for that for container B. For container B, the differential equation will be similarly dt2 divided by dt equals to A2 T1 minus 100. Okay, because the initial temperature was in the container B was 100, and this will be T2, not T1. Okay, so the second container, this is why. So whose solution is from the first example. What will be the solution? T2 equals to 100 plus P2 e to the power K2 T. Okay, this is equation number 4. Equation number 4. So when the metal, when the metal bar is immersed in the second container, is immersed in container B, the initial temperature was what? The initial temperature is T2 0 equals to 82. Sorry, 81 degrees centigrade. Because after 2 minutes, what was the temperature of the bar? 81 degrees centigrade. Then we immersed it in the second container. This is why the initial temperature for the second container B at time t equals to 0, what will be the temperature of the bar? 81 degree. So T2 0 equals to what will be 100 plus C2 e to the power 0, imply 81 equals to 100 plus C2. Therefore C2 value what? 19, right? Sorry, minus 19. Minus 19 C2. Second constant for the second container of the differential equation. Therefore, equation 4 reduces to 100 minus 19 e to the power A2 T. This is equation number 5. Just putting the value of C2. Now after 1 minute, the second container, after 1 minute in the second container the second container, the initial temperature pressure is T2, initial temperature is initial temperature of bar is 91 degrees centigrade. Okay, 91 degrees centigrade. Then after 1 minutes from the equation 5, after 1 minutes, T1 values 100 minus 19 e to the power k2. This equals to 91 equals to, because after 1 minute the bar temperature what, 91. So for this 91, we can find k2. So e to the power k2 equals to 100 minus 91 means 9. So 9 by 19. Therefore, K2 equals to ln 9 by 19, which is approximately 5 from 5 T2 equals to 100 minus 19 e to the power t ln 9 by 19. Okay, this is equation number 6. Now to raise the temperature up to now, setting T equals to, temperature equals to, at time T equals to 99.9 degrees centigrade. To get this temperature in the container, second container, that means in B, we have to find out the time T from 6. 99.9 equals to 100 minus 19 e to the power t ln 9 by 19. E to the power ln e to the power t ln 9 by 19 equals to 3.1 by 19. So from here, taking ln on both sides, t taking ln on both sides, t equals to ln 19 divided by ln 9 by 19. This equals to 7.02 minute. So from the start of the double dipping process, the total time until the bar reaches 99.9 degree in the second container is approximately what? 9 point. It will be what? This will be 9.02. 9.02 minute. This is the required minute.